So in this video I'm going to run through the questions for quiz 7. You're revising CC7, which is structure and bonding, stuff with like carbon and graphene and diamond, as well as structure and bonding in metals and simple molecules and ionic compounds. So there are a lot of 6 markers that come up in this topic. I've put 4 in the quiz. They're really not as bad as you might think. I've done them myself, so I'm just going to run through them with you. So the first one, you're given 3 substances. You're asked to figure out the type of structure and bonding. So they want to know, is it giant covalent? Is it metallic? Is it ionic? Is it a simple molecule? There are your 4 options. So you need to look at the properties and decide which one of those categories it falls into, and then explain how you know your answer. So a question like this, I would just go through it A, B and C. So A, I've said it's giant ionic. Okay, I know this because it's got a high melting point, and ionic compounds have a high melting point due to the strong electrostatic attraction between oppositely charged ions. The main giveaway though for this one was the fact that it conducts electricity when it is molten, so when it's liquid, but it doesn't conduct electricity when it's solid. That property is unique to ionic compounds. You need to be able to explain it. So you can conduct it when it's molten because the ions, and make sure you're mentioning ions here in an ionic compound, the ions are free to move, but it can't conduct when it's solid because those ions are no longer free to move. So it's the conducting electricity part that told me it was definitely ionic. The next one, you can see it still has a high melting point, but this time it conducts when solid and when it's molten. So this one is going to be metallic. Okay, and I know it's metallic because it's got a high melting point due to, I need to finish that off, due to the strong electrostatic attraction between positive ions and delocalized electrons. Okay, so these 2 answers are similar but slightly different. This one between oppositely charged ions, this one between positive ions and delocalized electrons. And the reason it can conduct in solid and molten form is due to the delocalized electrons. Now you might have looked at that and thought maybe it was graphite, because graphite can still conduct when it's solid. Graphite's got a much higher melting point. Giant covalents have incredibly high melting points, higher even than 1500 degrees Celsius, so it's not going to be giant covalent. Their melting points are too high. The last one, I know it's simple molecular, A because the melting point is much lower, and B because it doesn't conduct electricity at all. So I'm going to say it's simple molecular. It's got a low melting point due to the weak intermolecular forces that don't require much energy to overcome, and it can't conduct electricity at all because it doesn't have any free moving charged particles. Don't just say it doesn't have delocalized electrons. Neither does an ionic compound, and it can still conduct. So your umbrella term for kind of ions and delocalized electrons, without having to name them both individually, is just saying no free moving charged particles. That would get you all 6 marks. If you look at the mark scheme, if you have to identify all 3 to be in the 6 mark category, and you just need to describe 2 of them in detail. So the one that you're most sure of, so just say you were comfortable with ionic and molecular, give that a really good go and write loads of information. And with metallic, if you're not sure, just maybe write 1 little sentence on metallic, and just stick with the information you're confident about, because you don't need as much information as I've given. The next question was a bit odd. I remember this came up, was it 2 years ago? And we weren't expecting this as a 6 marker. This is only a tiny little bit in your booklet about bonding models. But even though it wasn't expected, it's actually quite easy, and there's so much on the mark scheme that you can say. You just need to look at these different models. They're all for CH4, and tell me what the model shows you and what its limitations are. All right, so if we look at A, CH4, it tells you you've got 1 carbon and 4 hydrogens, which is the molecular formula. But beyond that, it doesn't give you any information. You don't know how the atoms are arranged. You don't know if they're single bonds or double bonds. You don't know what the molecule looks like in 3D, like where the atoms are arranged. So there's lots of limitations you can say. B is better, okay, because you can see that the carbon's in the center and the 4 hydrogens are around it. You can also see how the electrons are arranged, but again, it's a 2D representation, and even if you didn't know it, by looking at the models for D and E, you can see that methane is actually 3D, and A and B, they don't show that. Same with C. So C is showing me that I've got single bonds, okay, so it's better than A, but at the same time it doesn't show me how the atoms are actually arranged in 3D, so that would be your limitation of C. And then D and E, they both show you that 3D structure, so you get that 3D arrangement of the atoms, But E in particular, you can't see the single bonds, so you don't know how the electrons are arranged. You can't see that you've got single bonds. D is probably your best representation because you can see that you've got carbon and hydrogen. Well, they would tell you it was CH4, so you know you had carbon and hydrogen. You can see you've got single bonds, and you can see the 3D arrangement. But this, if you look at the mark scheme, if you can either say something about all 5 of them, or you can talk about 3 of them in detail and give those limitations. So again, there's lots of scope to still be able to pick up 6 marks, but essentially just say what you see, and anything reasonable will be credited. So it's not as bad a 6 marker as it might originally have appeared. The next question, you'll get this from your mark scheme, but it is worth 3 marks, and there's quite a bit you have to say. So you have to tell me that carbon is in group 4, therefore has 4 electrons in its outer shell, but it only forms 3 bonds, therefore there's 1 electron left over, therefore it's got delocalized electrons. So you can't just say it's got delocalized electrons, you need to tell me why. It's got 4 electrons in its outer shell, but it's only forming 3 bonds, therefore 1 electron is left over. So look at the mark scheme for that one. The next question, you're reacting calcium and chlorine to form calcium chloride, but they're saying that the individual elements have very different properties to the compound that they form, and again they want you to describe why. So again, you can do this in 2 different ways. You could go through calcium chlorine and calcium chloride individually, or the properties they want you to discuss are melting point and conductivity, so you can do them based on properties. I do them based on properties because it allowed me to kind of lump a few things together. So for melting point, I said that calcium and calcium chloride both had high melting points. Calcium chloride is ionic, calcium is metallic. They both have high melting points because they both got strong electrostatic forces which require lots of energy to overcome. Now the forces aren't the same. In a metallic compound, those strong electrostatic forces are between positive ions and delocalized electrons. In an ionic compound, those forces exist between oppositely charged ions. Because the whole thing is worth 6 marks, and I've got lots of other information to say, I don't need to go into that level of detail if I don't want to. Then I'm going to comment on chlorine. It's got a low melting point. Why? Well, it's simple molecular, therefore you've only got weak intermolecular forces, not as much energy is going to be needed. In terms of electricity, they'll tell you that calcium can conduct electricity always. That's because it's a metal. I don't need to say that again. I've already said it's a metal, so I'm just going to say calcium is delocalized electrons, therefore conduct when solid and molten. But calcium chloride, your ionic compound, yes, it has ions, which are charged particles, but those ions can only move freely when it's molten. They can't move freely when it's solid, therefore it will conduct when molten, not when solid. And then Cl2, your simple molecular compound, no free moving charged particles, will never conduct electricity. So again, I've given quite a lot of detail there. You don't need to give that much to get 6 marks, but I mean, if you know the content, you may as well write it all down and guarantee your 6 marks. The last one is on your allotropes of carbon. So you've got diamond, graphene and fullerene, and I want you to talk about them in terms of their relative, which just means compared to each other. What are their melting points like, how strong are they, and what about their ability to conduct electricity. So I've lumped melting point and strength together because you're going to be making the same points for both. So I've said diamond and graphene, they're both giant covalent, so they want in terms of structure and bonding, so their structure is giant covalent, so I mentioned that. They're giant covalent, therefore they're going to be strong and they're going to have high melting points. The reason is going to be the same for both. They've got lots and lots of covalent bonds, strong covalent bonds, which will need lots of energy to overcome because those covalent bonds are strong. So strong covalent bonds. Fullerene is a simple molecule, okay? I know it's got 60 atoms, so it's much bigger than something like CO2 or water, but compared to these guys have billions of atoms, okay? So to be giant, you're talking about millions, billions of atoms. Fullerene's only got 60, so it is a simple molecule. So it's a simple molecule, therefore it's got weak intermolecular forces, so strength and melting point will both be much lower than what you had for diamonds and graphene. In terms of electricity, in diamond, make sure you're phrasing this correctly. What sometimes you guys are right is there are 4 covalent bonds in diamond. That is utterly completely wrong. There are way more than 4 covalent bonds in diamond. The way you have to phrase a sentence is each carbon in diamond, and there are millions of them, has 4 covalent bonds, okay? Because each carbon is forming the maximum number of bonds, there are no delocalized electrons, therefore it's not going to conduct electricity. But in graphite, each carbon is only forming 3 covalent bonds. There will be an electron left over from each carbon, so you've got lots of delocalized electrons. You don't just say there's 1 delocalized electron. That's not true. You've got millions of carbons, and each carbon has a delocalized electron, so they will carry current. If we look at fullerenes, The carbon and fullerenes, they do only form 3 bonds as well. So there are delocalized electrons within a fullerene molecule. But your issue is, if I wanted to conduct electricity, I'd have lots of fullerenes. And even though the electricity can move within a molecule, it can't move from one molecule to the next. So if I had a beaker containing fullerenes, I'd need the electricity to be able to travel across that beaker and across those fullerene molecules, and it can't. So I'm going to say that fullerenes are poor conductors of electricity, because even though they've got delocalized electrons, those electrons cannot move between the molecules, they can only stay within. So there are your 6 markers. Okay, it's a lot of the same language used over and over again. Just be clear on the difference between ionic and metallic. That is a common source of error. The rest of the questions are on fuels. I think they are straightforward. The only one I'll potentially look at will be this one here, question 35. It's a calculation. You're told butane. So it's an alkane with 4 carbons, so C4H10, and it tells you to calculate the mass of carbon in 100 grams of butane. Okay, you're told the formula mass of butane is 58, but I'm concerned about how much of that is because of the carbon. So carbon is C4, so you've got 4 carbons, 4 12s are 48. So I would get percentage by mass, and if I work that out, I will see that 82.76% of butane is made up of carbon. Okay, and then you're asked here, calculate the mass of carbon in 100 grams. Because they've already given me 100 grams, I can translate this to grams straight away. So if I got 82.76% of 100 grams, it will be 82.76. I am told to give my answer to 3 significant figures, so I'm going to make that 82.8 grams. Okay, so because percentage by mass of carbon in butane is 82%, you're going to have 82 grams of carbon if you had 100 grams of butane. If you have any other questions on any of these, then come and find me before your quiz.